For centuries, humanity has gazed upon the crimson glow of Mars in the night sky, igniting dreams of reaching beyond our pale blue dot. We have sent robotic emissaries to explore its desolate plains and towering volcanoes, seeking signs of past life and the potential for future settlements. But what if our ambitions extended beyond mere footprints on Martian soil? What if we dared to envision a Mars transformed, its barren landscape revitalized by the lifeblood of our own planet water? Imagine a future where the rusty hues of Mars give way to vibrant blues, where ancient riverbeds once again flow with liquid water, and where clouds gather in a newly thickened atmosphere casting shadows upon sprawling oceans. This audacious vision, though seemingly ripped from the pages of science fiction, forces us to confront fundamental questions about our place in the cosmos and our capacity to reshape entire worlds. The sheer scale of such an undertaking boggles the mind. Mars, while smaller than Earth, still presents a formidable canvas upon which to paint our aquatic aspirations. Its surface area is roughly equivalent to all the dry land on Earth combined, demanding an unfathomable volume of water to achieve any significant transformation. And yet, the allure of terraforming Mars, of seeding another world with the potential for life as we know it, continues to captivate our collective imagination. But before we delve into the tantalizing possibilities, we must first grapple with the immense logistical hurdles and unforeseen consequences that such an audacious endeavor would entail. The journey from a red planet to a blue one is fraught with challenges that will test the very limits of our ingenuity and technological prowess. Water, the elixir of life, covers over 70% of Earth's surface, its vast oceans dwarfing our continents. It's easy to perceive this life-giving substance as limitless, especially when standing on a shore and gazing out at the seemingly endless expanse. Yet, beneath this illusion of abundance lies a sobering reality. Freshwater, the type essential for most terrestrial life, is a surprisingly finite resource. While Earth boasts a staggering 332.5 million cubic miles of water, the vast majority, about 96.5%, is saline water locked away in oceans. Only a tiny fraction, roughly 2.5%, is freshwater. And even then, much of it is trapped in glaciers, ice caps, and underground aquifers, making it difficult to access. The water readily available for human use represents a minuscule fraction of Earth's total water reserves. This scarcity of readily available freshwater is a growing concern on Earth, with increasing populations and climate change exacerbating water stress in many regions. The notion of transporting vast quantities of water to another planet, even one as tantalizingly close as Mars, raises profound ethical and practical questions. If we struggle to manage and distribute freshwater resources equitably on our own planet, how can we even contemplate diverting such enormous quantities to terraform another? Before embarking on interstellar water transportation, we must first address the pressing water challenges we face here on Earth. Only then can we begin to ethically consider sharing this precious resource with another world. The success of any interplanetary endeavor hinges on understanding the intricate celestial dance between Earth and our celestial target. Mars, our red neighbor, isn't a stationary target. Both planets are in perpetual motion around the sun, their relative positions constantly shifting in a cosmic ballet. This dynamic relationship necessitates careful timing and planning for any mission to Mars, especially one as ambitious as transferring water. Launching a spacecraft to Mars isn't as straightforward as aiming at its current location in the sky. We must account for the time it takes for the spacecraft to traverse the vast interplanetary gulf and ensure that Mars will be in the right position upon arrival. This is where the concept of launch windows comes into play. A launch window represents a specific period when Earth and Mars are optimally aligned to minimize travel time and fuel consumption for a spacecraft. These windows occur approximately every 26 months, dictated by the orbital periods of both planets. Missing a launch window adds significant time and cost to a mission. The spacecraft would have to wait for the next alignment, potentially adding years to the journey. Therefore, coordinating the launch and arrival of countless water-laden vessels to Mars would require meticulous planning and execution, further highlighting the logistical complexities of this endeavor. Section 4. Galactic Tanker Trucks, Transporting an Ocean Across Space. Let's assume for a moment that we've solved the ethical and resource dilemmas surrounding Earth's water supply. The next Herculean task involves devising a method to transport unimaginable volumes of water across the vast cosmic gulf, separating our two planets. Even at their closest approach, roughly 34 million miles apart, the journey poses a daunting logistical challenge. Traditional rockets, like those used to launch satellites and astronauts into orbit, are ill-suited for hauling such immense quantities of liquid. Their payload capacity pales in comparison to the sheer volume of water required to make a dent in Mars's arid landscape. We would need a fleet of water-bearing vessels dwarfing even the largest oil tankers, each capable of carrying millions of gallons of water. These gargantuan spacecraft, envisioned as colossal spacefaring tankers, would need to be assembled in orbit piece by piece, drawing upon resources mined from asteroids or the moon to minimize the need to haul materials from Earth's gravity well. The construction of such a fleet would necessitate unprecedented international collaboration and technological innovation, pushing the boundaries of aerospace engineering. Once assembled, these water-laden behemoths would embark on their interplanetary voyages, propelled by powerful ion engines or perhaps even more exotic propulsion systems, such as nuclear fusion drives, still confined to the realm of theoretical physics. The journey itself, even with advanced propulsion, would take months, subjecting the precious cargo to the perils of deep space, from micrometeoroid impacts to the relentless bombardment of solar radiation. Section 5. The Tyranny of Thin Air, Mars's Atmospheric Challenge. Safely delivering vast quantities of water to Mars represents only the first hurdle in our planetary makeover. Mars's thin atmosphere, about 1% the density of Earth's, poses a significant obstacle to retaining liquid water on its surface. The red planet's feeble atmospheric pressure has profound implications for the state of water. On Earth, we take for granted that water can exist in 3 states: solid, ice, liquid, water, and gas, water vapor. The transitions between these states are governed by temperature and atmospheric pressure. Mars's thin atmosphere disrupts this delicate balance. The low atmospheric pressure causes water to sublimate, transitioning directly from ice to water vapor, bypassing the liquid phase altogether. Imagine trying to pour a glass of water on Mars. Instead of pooling neatly at the bottom, the water would rapidly boil and evaporate into the thin atmosphere, leaving the glass as dry as the Martian desert. This phenomenon poses a significant challenge to our vision of a water-rich Mars. Releasing vast amounts of water onto the Martian surface without addressing the atmospheric deficiency would be akin to pouring water into a sieve. To transform Mars into a world where rivers flow and oceans shimmer, we must first find a way to thicken its atmosphere, increasing its pressure and creating an environment where liquid water can persist. This atmospheric engineering, a task of extraordinary complexity, lies at the heart of terraforming Mars. Section 6. A Martian Thermos, trapping heat to sustain liquid water. Mars's challenges extend beyond its thin atmosphere. Its frigid temperatures, averaging a bone-chilling -81 degrees Fahrenheit, -63 degrees Celsius, present another formidable obstacle to maintaining liquid water on its surface. Even if we could magically thicken Mars's atmosphere overnight, the planet's distance from the Sun and lack of a substantial greenhouse effect would still result in temperatures too low to sustain liquid water for long. Imagine transporting an ocean's worth of water to Mars, only to watch it freeze solid, transforming the planet into a gigantic icy wasteland. To prevent this scenario, we need to find a way to warm up Mars, effectively creating a planetary thermos to trap heat and raise the overall temperature. One proposed method involves deploying giant orbital mirrors strategically positioned to reflect more sunlight onto the Martian surface, much like using a magnifying glass to start a fire. These colossal mirrors, spanning miles in diameter, would need to be assembled in space, presenting yet another engineering marvel. Another approach focuses on enhancing Mars's greenhouse effect, a natural process that traps heat from the sun. By releasing specific greenhouse gases into the Martian atmosphere, such as carbon dioxide and methane, we could potentially initiate a warming trend, gradually increasing temperatures to a point where liquid water could exist. However, these methods come with their own set of challenges and potential risks. Deploying and maintaining orbital mirrors would be a monumental undertaking, requiring precise control and constant adjustments to ensure the reflected sunlight hits the intended areas. Artificially enhancing the greenhouse effect on Mars could have unforeseen consequences, potentially triggering runaway warming or disrupting the delicate balance of the Martian environment in unpredictable ways.